All right, I just wanted to continue the work that we had started in class with this particular problem. So we're just going to get it set up the way we had it. Okay, so these are the three currents and how I labeled them in the different branches. And so from the junction rule, we got this relationship, so this becomes one of our equations. And then remember we did a green loop, which was this left-hand loop. And so we started at the battery. We went from negative to positive, so that was a positive 24. Then when we go through resistor 1, we're going in the direction of current, so that's a loss of I1 times R1. And then we come down through the middle resistor R2. With the current, that's another loss. I2, R2 equals 0. If I put in the values for the resistances, we get this equation. And so this will be an equation we'll work with. And then we had the loop over here. We'll call that the red loop. And I chose that purposely just to do some different directions. We go through the battery from positive to negative, so that's a loss. We go up through resistor 2, opposite with the current, so that's a gain. And then we go through resistor 3 with the current, that's a loss. And through resistor 4 with the current, that's another loss. So I got minus 29, minus 3I2, minus 3I3, minus 4I3. And I can combine these two, so I'll do that before I'm done. And that becomes our third equation. So the issue here is I have three equations and three unknowns. And I'm going to show you how I like to solve these. I want to work with these two equations simultaneously, but I need them to be the same two currents as their unknowns. This one has I1 and I2, this one has I2 and I3. So I'm going to use this expression here to get rid of I1 in this equation. So I'm going to start down here. I get 24 minus 3, and then I'm going to replace I1 with I2 plus I3. Minus 3 I2. So we get 24 minus 3 I2 minus 3 I3 minus 3 I2 equals 0, which is equal to 24 minus 6 I2 minus 3 I3. Okay, so now I'm going to work with, this will be equation 1, and I will also work with this as equation 2. So let's continue that on the next page. So I had 24 minus 6I2 minus 3I3. That was one equation. And the other one was minus 29 plus 3I2 minus 7I3. Now, what I would like to do, I like to be able to combine, add or subtract these two equations, making the coefficient of one of my unknowns the same, so that then when I add or subtract them, that I just get rid of that unknown. And I noticed that these are just simple multiples of each other, so that if I multiplied this bottom equation by 2, and then I added them, I would get rid of I2. So that's what I'm going to do. So I'm going to take the top equation, isn't going to change. And the bottom equation will be minus 58 plus 6i2 minus 14i3 equals 0. And then I'm going to take this equation and add it to the one above it, and I'll get minus 34 plus 0 plus 17i3 equals 0. And so this allows me to solve for i3. 17i3, sorry, this was supposed to be a negative sign. 17i3 was equal to minus 34, so i3 is equal to minus 2. So the negative sign just means that the direction I chose was wrong. And that's all that it means. It's still the amount of current that's in that branch. And so now I'm going to substitute to find I2. Actually, I'm going to find I1 first. So I took this value right here. I took this, and I can just substitute it into one of my equations. I ended up putting it in here. Okay, so let's see that work. We get 24 minus 6i I didn't. Right. What did I do? Okay. (24) minus 6i2 minus 3i3 equals 0. And so I'm going to make i3 is equal to minus 2. So 24 minus 6i2 minus 3. And notice I got to put it in as a negative value. So I get 24 minus 6i2 plus 6 equals 0. So 30 is equal to 6i2. I2 is equal to 5. And then finally, I1 was equal to I2 plus I3. So it's 5 minus 2, and that's 3 amps. And so now I found all my currents. So remember, just to remind you, this was I1, this was I2, and this was I3. All right? So that's just showing you the algebra of how we would go through that. The next thing that we want to look at, the last thing for this chapter, is talking about RC circuits. An RC circuit is a combination of a resistor and a capacitor, which can either be put in series with a battery, and in that situation we're charging the capacitor, or they can just be connected together, in which case we're discharging the capacitor. And so we're going to look, first of all, at the situation where we want to charge the capacitor. So it's connected to a battery, a resistor, and a capacitor all in series. We start with a switch open, and the capacitor is not charged. And so what we would do is when we would close the switch, then the current will start to flow, and as it flows, the charge starts to build up on the capacitor. Now, the thing that is different about this scenario than what we've done previously is that the current actually will change as the capacitor becomes more and more charged. Part of that is because there's a potential drop across the resistor and a potential drop across the capacitor. The sum of these has to be equal to the EMF of the battery. As the capacitor becomes more and more charged, this is going to get bigger, which will require the potential drop across the resistor to get smaller, and the only way for that to happen is for the current to decrease. So this is a case where things are going to be depending on time. So first I'm going to sort of think about what happens the instant the switch is closed, and then what will happen after a long time, sort of thinking about the two endpoints. So at t equals 0, just when the switch is closed, now at that instant, there's no charge on the capacitor. The very instant we close the switch, because we're just getting started. And because of that, the potential drop across the capacitor is 0, which means the potential drop across the resistor has to be equal to the EMF of the battery. From that, the current that's flowing originally in the circuit is going to be equal to that EMF of the battery over the resistance. This is the initial current. If t is infinite, which is just our way of saying after a long time, at that point, the potential drop across the capacitor is equal to that of the EMF. At that point, it's fully charged. And in fact, if we use this relationship, the charge that the capacitor has is going to be equal to the capacitance times the EMF of the battery, because that is the potential drop across the resistor. But then, because of that, the potential drop across the resistor has to be 0, which means that the current at this time is 0. So those are sort of our endpoints. What we want to know is what's going to happen in between. So maybe it's not clear, but there's at least a hint that all of these quantities depend on time. The current depends on time, as well as the charge. And we want to come up with the expressions that tell us exactly how they depend on time. So we're going to start this, and we're going to do a loop. So if we go around the loop, we go through the battery with a potential gain equal to the EMF of the battery. Then we have current through the resistor. This is because it's changing, is why I used a little I. And then the potential across the capacitor is Q over C. The current is the derivative of charge with respect to time, equals 0. And essentially what we have is a differential equation. So we're going to sort of separate variables to solve this. I'm going to find a common denominator here. Okay, now we are going to separate variables. That means we have to get all things involving Q on one side and everything involving T on the other. And we just sort of fuss around a little to make it a little easier to work with. Okay, and now we're going to integrate both sides. We're going to start at time equals 0 and go to some arbitrary time. When we begin at t equals 0, there's no charge, and then we let the charge reach some value q at some arbitrary time. So those are our limits of integration. So oops. This side is pretty easy. It's minus t over rc when we integrate it. This one, because it's dq over q, is a natural log. Now, in order to get rid of the natural log, we rewrite this as e to the minus t over rc is equal to q minus ce over ce. Now I'm going to rearrange things. So q as a function of time is equal to ce 1 minus e to the minus t over rc. And if you remember, this is q max. This is the maximum charge the capacitor can get. We could write this as big Q 1 minus e to the minus t over rc. So we have to sort of think about what this looks like. Basically, this is a value of charge that's exponentially sort of approaching. This is Q, and this is T. The charge kind of looks like this as it gets bigger and bigger. So we could, sorry. And if we want to figure out what does the current look like, it's the derivative of charge with respect to time. So remembering that Q is equal to CE, 1 minus E minus T over RC, dQ dt equals CE e to the minus T over RC times 1. And if you remember, this was the initial current when we time equals 0. And what the current looks like with over time is it starts at some maximum value and then decreases exponentially. So this is just kind of a prettier slide of what we just found. So when a capacitor is charging, this is how its charge depends on time. So the T is the time that's elapsed since we've closed the switch. This term right here, R times C, actually ends up being called the time constant. And if you actually do the dimensional analysis, this does have units of seconds, so that e to the minus t over tau has to be dimensionless. And so it's really kind of gives you an idea of how quickly it will change with that time constant. And we also did the current, and we found the current also has that time constant in it. It begins at some maximum value and then decreases exponentially over time. So that's for charging the capacitor. Okay. This is something you could look at on your own. I'll see if you can figure out the answer to this question. And then the next thing we want to do is we want to think about what happens when we discharge the capacitor. So when we discharge the capacitor, there's no battery, but we start with a fully charged capacitor, and we connect it in series with a resistance and with a resistor. And what happens is then the charge will start flowing and produce a current around the circuit. And so we sort of start off initially when the switch is open, we don't have any current, but all the potentials across the capacitor with its maximum charge. And then over time, the charge is going to decrease once we close the switch. And so we see in this picture. And you can see the little q's are representing the fact that those are different values of the charge because some of it's been used in the current that's going through the circuit like that. So if we're thinking about a loop rule here, we have minus I times the resistor minus Q over C equals 0. And I is dQ dt minus Q over C equals 0. And so dQ dt is equal to, times R is equal to minus Q over C dQ dt is equal to minus Q for RC. And now I'm going to separate my variables. dQ over Q equals dt for RC. And this is what we're going to integrate from start off Q naught, the maximum charge, to some arbitrary charge going from 0 to t. This is the natural log of Q over Q naught is equal to minus t over RC. That's what we get when we integrate and put in our limits. And if we had the natural log of Q over Q naught is equal to minus T over RC, can be rewritten as E to the minus T over RC, equal Q over Q naught. So Q, as a function of time, is equal to the initial charge minus RC. So the charge is going to start off with the maximum value and exponentially decay over time. The current is the derivative of charge with respect to time. And we get QE to the minus T over RC times minus 1 over RC. And this is with the current, how it depends on time. So let's look at some pictures of these. So this is discharging the capacitor. Starts off at its maximum value, decays exponentially with time. We still have this time constant in the exponential. So you can see that what resistor and capacitor we choose will have an effect on how quickly the circuit discharges. And then for our current, we have some initial value, its maximum value. We make it negative just to sort of indicate that when it discharges, it's moving in the opposite direction as it did from when it was charging. And it is exponentially decaying as well. So these are the relationships we have for the RC circuits. These are circuits that are anything that sort of happens on a regular basis, like your intermittent windshield wipers. You can use it for flashes, etc. And so that's sort of something that we would use in an electrical circuit.